Hello, I'm Eric Armengaud, researcher at CES Saclay. In this video, I will present the Baryon Acoustic Oscillation measurement with the Lyman-alpha forest that was carried out from the DR2 sample of the DESI Cosmological Survey. This presentation is on behalf of the DESI Collaboration and in particular of the people in the Lyman-alpha working group who contributed to this measurement. DESI is measuring spectra of a large number of galaxies from which we build a 3D map of the cosmic structures that make up our universe. There is a specific scale of around 150 megaparsec that's imprinted in these structures. As you can see in this illustration, this is the BAO scale. In practice, we measure it as a peak in the correlation function of tracers. And if you want to know more, please have a look at the paper and related video in this YouTube channel by Wendert and Reid. In the companion paper mentioned here, we present all DESI DR2 BAO measurements summarized in this plot, where we see the BAO scale as a function of redshift relative to a model which best fits our data. Measurements at redshift below 2 rely on galaxies, but for redshift above 2, with the data from the current main DESI survey, the density of these discrete tracers is too small to measure BAO. Instead, we rely on the Lyman-alpha forest. That's the violet point. The corresponding isotropic BAO peak is shown there, and I will focus on that now. The Lyman-alpha forest is a set of features in the optical spectra from distant sources, like quasars, produced by the resonant absorption of neutral hydrogen located in the gas between the source and the observer. Thanks to the redshift effect, a cloud of gas produces an absorption which we see at a wavelength whose value depends on the position of this cloud along the line of sight. From the associated transmission, shown here as the violet curve in this plot, we can trace the fluctuations of matter density on large scales. In DESI, we observe a huge number of these forests over a wide footprint. However, this is at the price of relatively noisy measurements, which is illustrated in the plot below. The DESI DR2 dataset results from 3 years of observations. It provides an unprecedented sample of around 800,000 spectra with the Lyman-alpha forest. And for our measurement, we also use 1.2 million positions of quasars at redshift above 1.8. With respect to our previous measurement, DR1, as you can see on this plot, many of the spectra were reobserved up to 4 times, which means that the signal-to-noise of our data is significantly larger than DR1. As another major improvement, we use a new catalog in order to filter out the so-called DLAs that are contaminants in our data. We improve our algorithms to identify them. This is described in detail in this supporting paper led by Alison Broadzeller. To measure the BAO from this Lyman-alpha sample, we build a compressed observable, which is a set of correlation functions. As illustrated in this picture, we consider pairs I, J of Lyman-alpha transmission signals from different lines of sight. And from those, we derive the autocorrelation function Xi using a weighted average. Xi is a function of both the longitudinal separation, or parallel, and the transverse separation, or perp. Actually, we measure 4 correlations from different subsamples. They include Lyman-alpha forest autocorrelations, such as the one shown here, but also cross-correlations of the Lyman-alpha forest with quasars positions. Now I turn to the model we use to interpret Xi. On large scale, this is essentially the Fourier transform of the linear matter power spectrum with some bias and error terms. And the 2D plot here shows this model for Xi as a function of R perp and R parallel. And you can see the BAO bump along this dashed line. Similarly to what's done for galaxies, we parameterize the position of this bump with 2 rescaling parameters, alpha par and alpha perp, defined here. They are our main BAO fit parameters. However, that's not the end of the story. We also have to include contaminants in our model. The 2D plot now includes their effects. And in particular, you can see there are some spurious peaks there along the R par axis. They are due to metals, silicon transition lines. And with respect to DR1, we've brought some technical improvements to model this important contamination. Last but not least, to use the Lyman-alpha forest, we must take into account the intrinsic continuum in the quasar spectra. We perform what's called continuum fitting. The resulting effect on Xi is very large, as you can see how the 2D plot changed. But this is well modeled by a so-called distortion matrix applied to Xi. For this analysis, we have improved its calculation, specifically by taking into account the evolution of biases with redshift. Now, the Xi you see here is the best fit model to our DR2 measurement. I show it again here. And for visualization only, we split this 2D area in 4 quadrants, which are called wedges. And we show 1D plots of Xi with a different color for each of these wedges. The data points and best fit curves are shown here for the Lyman-alpha autocorrelation on the left and the cross correlation with quasars on the right. The fit is done fully in 2 dimensions. It has 17 parameters, including the 2 alphas of the BAO peak, and we get globally a good fit with a satisfying chi-square. However, you may see especially this place on the wedge plot where the curve doesn't seem to go through the points. So we looked more closely at the fit residuals. Here they are shown in 2D, and you can see this kind of outlier related to the feature in the wedge. We ran dedicated random realizations of Xi with the bootstrap method to model fluctuations and found that actually 15% of these random realizations had such an outlier. So we conclude that this apparent disagreement is not statistically significant. And the plot shown here on the right shows some of these random realizations, so you can see their fluctuations. All these measurements was performed with a blinding strategy, identical to the previous DR1 measurement with a different seed. Before unblinding, like in DR1, we made a series of validation tests, first with MOX. We improved our MOX with respect to DR1, including more statistics and more realistic properties. In particular, we investigated the effect of quasars redshift uncertainty on the BAO. Those mocks and tests are described in this supporting paper by Laura Casas, and you can also find a related video on this channel. Second, we use the data to perform a set of splits and analysis variations. The figure on the right shows how our inferred alphas change for some of these variations. The red contour is our statistical error, and the gray region is 1/3 of it, so we want variations to stay inside it. For example, the green point correspond to a new variation that was proposed to mitigate the impact of quasars redshift uncertainty I was talking about. Also, the cyan point shows a fit where we add some arbitrary broadband polynomials to our model for Xi, and you've already seen it represented by those dashed curves on the wedge plot. So we did quite a lot of those variations and tests, and all shown are here for the record. So you can see how stable our BAO measurement is. Finally, here are the unblinded results. We measure alpha par equals to 1.002, alpha per equals to 0.995 with a % level error. Given this level of precision, we were now at a point where we may worry about the shift of the BAO peak position due to the nonlinear cosmic evolution. This effect is well studied for galaxies, but it's still poorly known for the Lyman-alpha. We only have 2 recent publications at hand starting to quantify it by Francesco Sinigaglia and Roger de Belzunce. I show the references here. At this stage, we decided to take this effect into account by adding a systematic effect of 0.3% to our alphas. In the end, I show on this plot our measurement of the BAO distance scales, dm and dh over rd. This is a remarkable 0.7% precision measurement of the isotropic BAO scale at a redshift 2.33. The plot also shows the improvement with respect to DESI DR1 and its consistency, and compares our results with CMB, both for the lambda CDM and dynamical dark energy models. To conclude, with DESI DR2, we have an unprecedented Lyman-alpha forest dataset from which we extracted a BAO measurement at redshift 2.3 with a precision well below the percent for the first time. Beyond this gain in statistics, I also presented a series of improvements for this measurement, which are summarized here. I thank you for your attention.